Hi, and welcome back to the third video in this second lecture on Covidenomics. In the last two videos, we've looked at the standard SIR modelling for a pandemic. What we're going to do in the next two videos is look at the limitations of that modelling. We're going to start off in this video by thinking of the limitations with regards to the information and the actual structure of the model, but it's not really going to be from the economic perspective. In the next video, we're going to bring in human behaviour, the heart of economics. Think about how that will change the SIR model. So let's just quickly remind you of our basic SIR model. The number of people who are infected in period T+1 is just the number of people who were infected last period, plus the number of people, those who were infected last period, infect, which is simply this beta or reproduction number times the proportion of the population who are susceptible to infection in period T, and then take away the fraction of last period's infected people who recover. So it's last period's infected plus new infections minus recovered. It's a random infection model, so you can think of it that an infected person bumps into other people randomly and infects a proportion of them. So we have our reproduction number made up of an exposure rate, that's the number of people an infected person bumps into on average, times an infection probability, the chance that when you bump into somebody, they become infected. We have a constant rate of recovery, which is simply given by gamma, and then our total population is simply made up of these three groups. You're either susceptible, or you're infected, or you've recovered or died. So let's think about a few of these things. Firstly, let's focus on our reproduction number, beta. We've got the exposure rate and we've got the probability, but they're both given as constants in the simple models we've looked at. In reality, you're going to be talking about a distribution. So different people have different probabilities of bumping into people and also passing on the disease if they do bump into them. So we really need to think of E and P as coming from some form of distribution. Or in other words, we need to move from what's a very static model to what's called a stochastic model so that we can start getting some distributions, some probability distributions around what's going to happen to our infections. Because let's face it, we don't know perfectly what the infections are going to be next period. It's a probabilistic, it's a chance. Next, we can look at our recovery rate. Well, in the standard SIR model, you don't actually distinguish between recovered and died. Sort of matters if you're infected. More importantly, we're assuming that everybody recovers in a certain period of time, but clearly that's not the case. Different people recover at different rates. And finally, we've got our population shares. Those who are susceptible, those who are infected, and those who have recovered. But we assume that once you've recovered, you can't become infected again. And that's not always true with viruses that can mutate. To see why these assumptions are important, and to see why we need to extend our basic SIR model when we apply it to the real world, this is a snapshot that is produced every day, at least whilst I'm preparing these slides, by the Australian government of the situation of COVID-19 in Australia. So let's focus in on a couple of things first. If we go up here to the daily number of reported cases, you'll notice it's starting to spike up again around the 7th of July. That's reflecting that we've got some new cases, a new outbreak in Victoria, which is why we're being locked down again. More importantly for our purposes here, let's focus in on a couple of the differences in demographics. The one down here looks at cases by age group and sex. Notice that you've got the most infections occurring here among younger people. There's slightly more infections among younger women than among younger men. And the number of infections goes down as the age level goes up. Now, part of that's just driven by population demographics. There aren't that many people over 80, but it's quite clear there are more younger people infected than you would expect purely by population shares. Let's now have a look down at the deaths. If you look at the deaths, then an immediate thing that strikes you is those young people that are infected don't die. The deaths are mainly among the older people. Now that's actually not usual for a virus and a pandemic. For example, the Spanish flu that we've talked about back in around 1918, 1919, it actually killed young people just as much as it killed old people. It didn't distinguish. COVID-19 does. COVID-19 tends to kill older people. The other thing to take off this bit of a graph here is that if you're a man, you're more likely to die than if you're a woman. These statistics aren't unique to Australia, so here we have US deaths from coronavirus up to about the middle of June, and you'll notice they form a similar pattern in the sense that younger people under about the age of 50 very unlikely to die of COVID-19. But if you start looking at the older generations, older people die when they get COVID-19. In the Australian numbers, we saw that men are more likely to die than women from COVID-19. Let's look again at the US numbers and look at the deaths by race up until about the middle of June. You can see from the numbers here that black Americans make up about 23% of deaths, but they only make up 13% of the US population, which means that they are overrepresented in the people dying from COVID-19 in the United States. Now notice that none of these facts that we've got from the data on COVID-19 are included in the SIR model, and if we want that model to be accurate in predicting the progress of a pandemic, we need to extend the model to include the difference in infections, for example, between different groups, the differences in deaths between different groups. Now, fortunately, a bunch of very smart people have done all of that. The second thing, though, to point out is the importance of these facts for policy. Now, I'll come back to the young having more infections than you would expect in my next video. But let's look at the next fact. The old die more than the young. That may mean that when we're thinking about policies to deal with COVID-19, we may want to focus on policies that isolate the older parts of the population, the parts of the population that are more vulnerable. And many countries have done that. Aged care facilities in particular have been isolated to make sure that the older residents in those facilities remain safe. It also has another less pleasant policy implication. If COVID-19 kills older people who may be in their last few years of life, is it less important than if it killed younger people? We're going to talk about that in a few lectures. It's an issue we cannot avoid. The next one, let's look at the race issues that are highlighted by our US data. Why do some groups die more than other groups? Well, one thing is simply fitness and poverty and the connection between health and poverty. It's quite clear that COVID-19 is more deadly if you have other physical conditions, such as diabetes, such as hypertension or heart disease. You're much more likely to die if you then contract COVID-19. You're much more likely to have those conditions if you're part of certain demographic groups who, for example, are simply more susceptible to diabetes, such as South Asians, or if you have poor living circumstances. So diabetes and heart conditions are much more common among people who are poorer. So COVID-19 will tend to affect poorer populations more than it will affect richer populations in the same country. So we've seen that the basic SIR model needs to be extended in a variety of ways. Firstly, to cover beta, the infection rate, we've seen that the young tend to be infected more than the old, so beta is not constant over the population. In terms of the people who have recovered, we've seen that the old tend not to recover. They tend to die more than the young, and that needs to be incorporated into our modelling. How else can we think about the recovery rate? Well, one other issue we need to think about is the hospital care that you can get in different countries. If you get COVID-19 and become critical, you need hospital care. But your chances of getting that hospital care are going to differ in different countries. So the data here from the OECD shows the number of hospital beds per 1,000 people. Australia is this one here. We have 3.9 beds per 1,000 people. You'll notice some other countries, UK and Canada, are a bit lower, as is New Zealand, but you'll notice that some others are quite high. And that's going to matter for recovery rates, because if the pandemic accelerates, you're much more likely to have your hospital system overrun if you're down at the left-hand end of this graph than if you're up here in the right-hand end, along with Germany, Japan and Korea. Next, let's return to this infection number, beta, because we're going to see that neither the exposure rate or the probability of infection really are constant with different people. Let's start with the exposure rate, E. Different people actually have different levels of exposure, in part because some people are asymptomatic. In other words, they don't show any symptoms. So they can't take precautions to avoid interacting with and potentially infecting other people because they don't know they have the illness. Perhaps the most famous person in history in terms of an asymptomatic carrier was for typhoid. And it was a person called Mary Mallon, who's sometimes known as Typhoid Mary. She was a cook to wealthy New York households back in 1906. And she had typhoid. However, she showed no symptoms of typhoid. As a result, she ended up infecting probably around 50 people before it was realised that she was the cause of the outbreak of typhoid. But it's not simply asymptomatic people that have a higher risk of infecting others. Different people will have different exposure rates and they'll have different probabilities of passing the virus on. They're going to depend on things such as cultural factors, how large your family is, how large your network of friends is. It's going to depend on your occupation. Are you in an occupation where you interact with a large number of people? Let's give a simple example. Typhoid Mary wasn't the person who passed on and caused the most deaths from typhoid in New York in the early 1900s. A person called Tony LaBella, who was a food worker in New York City and continued working with typhoid, is thought to have infected more than 100 people. Before we get too excited and start extending our SIR model to come up with better predictions for the government, we've actually got to recognise that early on in a pandemic, the government faces a huge information problem. It doesn't know about asymptomatic carriers. It doesn't know whether people who have recovered can become reinfected. But it doesn't even know the most basic parameters of our model. For example, we don't know how long it will take for people to be infected early on in a pandemic. We don't know early on in a pandemic what the death rate's likely to be and who's likely to die. We don't even know early on in a pandemic what the initial reproduction rate, our beta, actually is, because that's data that's being generated in real time. So early on in a pandemic, governments face a huge information problem, and that's going to affect their ability to react to the pandemic. Indeed, they don't even know that there is a pandemic going on. Tyler Cohen has an article from early March, so before most countries locked down, where he notes that there are two different schools of thought at that time about COVID-19. There's the pandemic school that says it looks like it's increasing at an exponential rate. We've got a pandemic here. But there's also the people who remember back and think, wow, we've been here recently. We had the SARS outbreak, we had the Ebola outbreak, we had the Zika outbreak. We got all of those under control pretty quickly. They didn't spread worldwide, they remained contained. In hindsight, that second group were wrong. Unfortunately, on May 4th, when Tyler Cohen wrote the article, nobody knew. And that's the big problem early on in a pandemic. How do you respond when you don't know pretty much anything including whether you've got a pandemic. In the next video, I'm going to make life even harder for governments and for people trying to predict the pattern of a pandemic, because I'm going to start introducing human reactions. In particular, we're going to see how economics provides a very simple reason why younger people have more infections with COVID-19 than older people. And it's related to that death statistic that we also presented earlier in this video. But let's do that next time.